Hope will be a continuing series of symposia that are driven by and organized by students. These are our first batch of PhD in design students. It's their agenda and their show, and we're very pleased and kind of grateful to the AA for encouraging them to do this. They have chosen the topic and the speakers, and they will, in their own work today, present their research questions. The majority of them are somewhere around halfway through their doctorate, which is about the time, PhD in design, when the questions become really sharp and focused. And we're also very grateful for our distinguished guests, most of them old friends too, Branko and Mark, Greg, Axel, you'll know, and Luca and Hotta. I just want to say a few words about the kinds of topics that we're exploring in the PhD in Design program. We're using all the systems and methodologies that you're used to in computational design for the design of buildings and in some cases of cities. But we're also starting to address what you might call cultural phenomena. And we're super interested in developing ideas about the city that extend beyond the idea of it just being a spatially extended kind of material system. Some of them are dealing with perceptual phenomena. Acoustics, I think we're going to have on the first one from Merate. And the phenomena we're dealing with are intimately coupled to behavior and to life in the city. But this presents us with certain kinds of problems that can we use the same techniques, the same kinds of maps and computational systems that we've used for material system design and for building design. And maybe there are questions, maybe we are not entirely convinced that some of these methodologies are immediately transferable. We're also particularly interested in things that can be measured but are not tangible. That is, they affect how we see things, how we behave, how we perceive spaces, how we move through them. They affect our lives and we deal with them all the time automatically. And we're convinced these do have an effect on the dynamics of the city, ultimately in the long term on its morphology, on the social structures, and perhaps more appropriately and in a more complex way on the idea of cultural identity in cities. But what we've tried to do today is they will present their questions as tightly and precisely as they can, and we hope that we have, and that you as the audience will join in with our distinguished guests in the discussion round, which they will lead and ask certain questions for. So the last kind of phrase that I'll leave you with is that the kinds of topics you'll see today, we think are an index. They're kind of indexical phenomena of the culture of the city. But we're not going to do very, very much, if any at all, of critical theory. We're going to be trying to talk about measurements and about the systems of representation and how we can use those as drivers or in generative techniques. So I'd like to say personally a big thank you to Ken and Merate, to Elif and Francis, to Ali and Arturo. They're the pioneers, the experimentalists, and it's their show.
Thanks, Mike. We're going to start out with a few things. I just wanted to say a few things. If we can keep things in the same time-allotted space. I know we started a little bit late, but we are going to try to keep within the hour because it's a long day. Also, I would like to introduce myself and my colleague. My name is Barakat. My colleague is Kensuke Hotta. And another thing for people that are in the audience or they have questions, and I'm the only one that can say this with a straight face, we have a hashtag on Twitter set up with called AA Translate Intangible if you have any questions for our guests throughout the day. Also, I guess we can start our session. This is the first session, and it's called Spatial Cognition and Performance Systems. Yeah.
Hello, this is Kensuke. So this session will look at interdisciplinary domains like spatial conditions, cognition, and intelligent designs. The architectural field faces challenges of expressing and documenting non-linear design processes that incorporate mathematical and biological in linear media, like in print. Okay. Also, when design becomes intelligent or aware, the design field borrows terminology and analogies from psychological and social sciences. So here, we are trying to develop common bases as design methodologies cross-path with ephemeral and temporal paths.
Okay. In a sense, we are going a bit quick right now because we're late, but in a sense, this is the extreme of what is intangible of the day. And I'm going to go ahead and, yes. Okay, I'm going to go ahead and welcome our guests, Luca, Dellatore, and Had Lipson. They will be following us with presentations, and then we will be sitting over there trying to discuss with them with intelligence. So I'm going to start up with an overview of my work, and then Kensuke will follow. I am working with urban sonic networkings. What I am looking at this stage is a set of research questions. I'm looking at urban design and how acoustic design can be integrated into that field. So I'm going to start up with senses, and essentially the people do not just see, they also hear and they taste. And if we look at our senses, they are very connected. Even though we only design for visual senses, we actually hear everything. They are connected to in our brains. So I'm just going to show something that we all know is the connection between taste and smell, and you can tell right away that we all know that connection. We grew up that way, and normal people just have that. Also, if you look at this one, she's trying to crunch and she's not very happy. But if we go to the idea of connecting sound and vision, people, when they listen to something, they actually get a visual image or an idea, or it reminds them of something. And that is actually something called programmable sound. And I am going to be try to use that in my design to attenuate and manipulate sound in an urban space through materiality and geometry. If you walk down London here in South Bank, you will hear a set of sounds, and this is what you hear. And everybody knows, like church bells, we know the different sounds, they give us an image. We don't need to look at the image to actually know that this is a street. We know that this is a church that's happening, that we're walking by. And so this is what I'm trying to do. I'm trying to hear the urban design in a certain way. So, and to my actual idea is that if we look at space, it has walls. But if we hear it, it could be just a bubble. And that bubble is what we call acoustic arenas. If we design through sound, then acoustic arenas will make spaces that do not require a physical barrier. And that would be through geometry. So the idea is that if we look at a concert hall, the physical size is what we know. But once something like an event like this audio, the audio space, or I am the sonic event, and I am creating a space that is sort of shrinking your own audio space. And this happens in cocktail parties, it happens on the edge of a cliff. It is a phenomena, and I'm going to be using that to design oral arenas. There is a set of data sets that I'm looking at, different types of spaces, and how you can navigate through these spaces, and how these spaces affect people in the sense of physically and psychologically. These are the data sets. I'm not going to go through them real quickly. I'm not going to go through them because we need to get through this quickly. But the idea is that I'm taking these data sets, turning them into mathematical equations. These are images representing the mathematical equations that are being implemented into a time-based process. And from that, we should go into, and I have started right now, going into urban space. And the idea, as simple as it could be, is if you have the idea of a landmark, there's also something called a sound mark. The sound mark is a big space within an urban place, and anyone that hears that space actually belongs to that arena, and historically, that means that created a city. So if we look at the last part, the first, if we look at the minaret on the top, that is what we call a sound mark. And at this moment, I am looking at an old city and how the trajectory of wind would actually change or deform the acoustic arena. And right now, unfortunately, I don't have the code, but it's very promising, and it seems that where you can see the wind coming from the west and the northwest, and where the church is, that red spot at the bottom, you can see that the morphology of the city actually sort of grows around the distorted bubble of the acoustic arena. Okay, that is in short what I've been doing, and I'm gonna let Kensuke talk about what he's been doing. Thank you.
Hello, this is Kensuke. I'm also researching about architecture, but my proposal is more architectural, the building. But also I'm trying to design the control system as well. The intelligence is really difficult to define. Firstly, I'm going to introduce my proposal. This is a winning project in Japan. I got first prize. Actually, this is a station. This architecture consists of lots of the tensegrity component, but those are kinetic. And one reflex is global reflex, and another is the local reflex. What I am expecting in here is to make architecture programmable, both meaning of programmable. One is functionally, architecturally programmable. The another is the control system, computer system. What should I say? The control system is also should be also programmable. As you can see from here, three different cases. For example, the first one, the upper one, is station. The second one is gathering people inside the center of the space. The third one is scattering. The person is scattering the space. So now today I have really limited time, so I'm trying to focusing on the control system, the intelligent control system. For example, first one, the robot arm, there is 5 servos on the hinge, but they are not connected well. Because this is okay, because this is simple machine, but Oops. Sorry. On the other hand, architecture machine is, oops. Yeah. Okay. In this architectural proposal, I use tensegrity structure. As you can see, the cause and effect is really complex. If I put the other side, you can see the end of the side is deforming, which means it's really difficult to control. So my strategy is to make virtual mathematical model. Firstly, the secondary put physical engine. The thirdly, put generative algorithm to control. Oops. Where is it? Sorry.
Yeah, that's a good question. Where is it? Okay. Is this gonna come? Just keep talking.
I'm sorry.
Technical difficulties. This is the next one, right? Yeah?
Yeah. This is a demonstration to put the physical engine. Actually, this is ready-made. Actually, this work is really inspired by that Lipson's work and Mike's Emergence. Okay, this is the first one. Oops.
Can just move pan. Oops. Fuck. Sorry about this. Okay.
And then here, I'm trying to use genetic algorithm to control everything. As the same way, I just switch on the physical engine first. Then you can see, as I said, the tensegrity structure is really complex. The parameter is, there is a lot of parameters. It's really too difficult to control manually. So I put the engine, genetic algorithm engine, to optimize this shape. The fitness criteria is the maximum distance, actually z vector. I am expecting this kind of shape, the maximum distance z directions. And as you can see, it's getting better. And right side, upper part, you can see the population's distribution. It's getting shrinking. Now speed is 300%. Actually, the system is ready-made, but it's quite powerful. So after 10 generations, you can see the shrinking. The population is almost. So now after 15 generations, we can see almost fixed. The structure is not moving. So finally, we got the fittest individual. So this is a genomes. But actually, this is not morphological optimization. I'm trying to find out the temporal situation of this structure. Okay, that's all. Thank you.
So we would like to invite Luca Dellatore right now to go ahead and start. He is an acoustical engineer and architect. He works at ARUP, and we're delighted to have him. I gotta go.
Thank you very much.
Hello everyone. My name, as Merate said, it's Luca Dellatore and I work at ARUP. And let's go up. First of all, I need to thank Merate for inviting me to this symposium because the subject is really interesting and is one of the things that we, on an everyday basis, we try to solve. So how can we make people understand how the sound is traveling through a space? How is the sound going to change the experience we have in a space? And it's an ongoing kind of relationship between us that are kind of technical and other types of engineers, architects, and also clients that they don't know anything about architecture in sense of technical architecture. So as you can see here, there is this pink noise spectrum. Is a pink noise. Why pink? First of all, because it goes well with my back of my business card. And the second thing is because this, the definition of pink noise is basically a type of noise that has the same energy across the entire spectrum of the audible sound. So it means that I like this analogy that I'll try in these 20 minutes to basically cover the entire spectrum of the methods we use to translate sound in something that is more understandable. So since I'm a bit thick, that was my first question, is sound intangible? So I went and I looked up in the dictionary, had kind of 10 minutes research, and I ended up with a couple of definitions. The first one was something intangible is something that is incapable of being perceived. But then if we listen to the Brits, then it's just by touch. But if we listen to the Americans, it's by the senses. I don't know if this is what I found in my research. But in that case, then sound is something we cannot touch, but we can perceive. So back to the third question, maybe is intangible, but it's not. For sure, it's something that it's a bit unclear to the mind because we don't see it. We don't see the way it travels, the way it interacts with the different material around us. So this is also why sometimes it happens that maybe you meet some acousticians that unfortunately they are taking advantage of this fact, and so basically they want to be kind of black magicians. So they kind of talk to architects and they basically say to architects and clients that sound is a bit of a mysterious thing, but actually it's not. It's just a scientific phenomenon that can be explained, so don't believe them. Okay, what I found in my experience in the acoustic world is that we need to talk to other people. So this is Hotta Hall in Cardiff. It's a recording studio and a hall for symphonic orchestra of BBC Wales. And this is how everyone would look at the hall. But then if you use your acoustic goggles, this is how we see it. So you can see that there is a difference between the way we look at a space the first time we receive the drawings from an architect. So we look at the acoustic characteristics of every surface, and we kind of trying to identify by mixing our experience and while reading the drawings, trying to understand how the sound is going to travel in this room. And in a way, I think that from our side, we need kind of to get closer to the way everyone is speaking and try to make us understand a bit better. Because, I don't know, I see sometimes there are long reports from acoustic consultants that are just kind of 50 pages of words that as soon as someone opens them, it's really difficult to get any information out of it. So when I joined ARUP, this was one of the first halls we had to design that I was involved. So we tried to develop some scripts in order to identify which were the reflection from. Basically, this is a 3D model of the hall. We have a set of suspended reflector above the orchestra, and we wanted to know which was the coverage of these suspended reflectors. Unfortunately, there's always some problem with the video, so I'll go. So we can see that basically we developed the script, but the scripts were a bit slow, and then the scripts were something that were separate from parametric design. So every time we had to run a new model, we had to manually change all the panels. So we were able to generate images like this one in order to show to the client which was the best design in order to achieve a good coverage of sound caused by the reflector above the orchestra. These 4 balls basically represent a group of musicians. But then we started using other techniques like computational design, like the use of grasshopper and rhinoceros that speed up a lot the analysis time. And so we can generate ray tracing quite quickly. And we can also change the shape of the panels and see straight away, like the curvature and height, and see straight away which is the effect in the room. This is not something that is valid only in a closed environment. It's something that, as it was said before, it's something that can be applied to whatever situation also outside. And then we started to add additional information to this graph. As you can see at the bottom left, at the bottom, we have some colors that tells us how these reflectors are interacting with sound, because different frequencies, different types of sound, they interact in a different way. And in a way, yes, this representation is a static representation, while the sound is not a static representation. So we have to kind of produce different images to show how this is, how is the dynamic link between the surfaces and the room. Still using parametric design, we find that is really useful to apply the optimization techniques to acoustics using mainly geometrical tools. Okay, it's not, yeah, it's working. So basically, in this case, the software is just using the Galapagos genetic algorithm plugin in Grasshopper, trying to optimize the surfaces of the 2 balconies in the hall, just to get as much sound as we can in the top balconies. This is one option. Or we can use other more powerful tools like MATLAB, that has a lot of different optimization techniques. And it's quite easy to link MATLAB with Rhinoceros and Grasshopper, and basically they can dialogue even on 2 different computers using the network, so they send each other messages, and this has been tested already on different projects. So the good thing is that we were starting from the first option with few reflection ended up on the balconies that are always the worst places for acoustic perception, because they are so far from the stage, and so it's not that good. To a situation where we can see that after a few generations we have a lot of reflection ended up on the top balcony. This is not enough for us to understand if the acoustic is good or not, because what we do is that we do a geometrical optimization, simple in Grasshopper, and then we use the same model and we put it in software like Audion or Cat Acoustics, that are software that are able to predict other acoustic parameters that are a lot more complicated, but when you run simulation with the software, it takes a really long time. This is another project I worked on, and it's the design of a portable acoustic shell designed by BFLS. And we did the optimization of the internal surfaces in order to project as much sound as possible towards the audience. So we did some studies on comparison. So on the left, we see how is the sound plot without the shell, and on the right is with the shell. So you can see that the sound before was spread in kind of in every direction in the same way from the stage, that is the 4 dots, is now kind of projected forward. And the funny thing about this project is that then we had to patent it. And for the patent, they just accept black and white pictures. So all the colors that are telling the story, they were not good enough for them. And so we ended up with these contour lines that if you don't have at least 1 hour, I would say, you just don't get any information out of them. But this was just my complaint about the patent office. This is a project in London, is the Milton Court recital hall for the Guildhall School of Music and Drama, and it's a project we are doing with RSWL. It's just an example of how this visualization of sound is something that is really important for us to not just to communicate results to clients or to show to architects why a certain surface with a certain material and angle is better than another one. But when we see such a formula, it's like it's difficult to visualize how this formula is linked to the model above. So basically, we try to. This is basically ST early is just briefly is the support that a musician has on stage while playing. So basically, he needs to receive a reflection back to himself. So if he hears himself, he can play well, and it's something really important in a concert hall. So basically, this is the visualization of that formula. So what does it mean? That the support on stage is basically the sound that the green sound is the delayed sound, the sound that arrives from the room, divided by how much sound is the direct sound, so in the near proximity from the musician. So what do we need to know in a new hall when we do the design? Which are the surfaces we can modify in order to improve that parameter? So this is all we need to look at. So we will be interested in changing the surfaces in green, but not that much in changing the surfaces in gray, because they are not calculated in this parameter. And this is just one of the examples of the many parameters we need to analyze in order to make acoustic good in a certain space. Another thing that it's a bit more difficult to analyze is that when you have a sound source, every sound source has a different directivity. So the sound is not propagating from a sound source in every direction in the same way. So this hall is in the Royal Welsh College of Music and Drama, designed by BFLS, that we have worked on as well. So when we have a quartet playing this hall, every instrument is projecting sound depending on the frequency in different direction. So we did this exercise trying to understand where was the sound going to make a better analysis of the whole. So basically, this is a 2D image of the sound propagation for an instrument, and this is a 3D image of the sound propagation from a quartet, because you have the interaction of 4 instruments at this point. Now, I just need to plug in the sound. Yeah. Hopefully it's not too loud. Maybe a bit. No? Nope. Let's yeah, but now the sound. Sorry for the technical glitch. So as you could see, there were these kind of wobbly things moving. And basically, what are they? They were the representation of the sound in different frequencies, kind of low, medium, and high, going in different directions. But it's really clear that usually the most powerful instrument on a quartet, the main instrument, is the first violin. And as you can see on the left, there is this big bell higher, and that's the first violin that's playing with the instrument in the position. The sound is going very high, as you can see. And so this is very informative way to see it, and it was the first time I've seen it myself. So how did we do that? Basically, we had a quartet that was recorded in an anechoic room. An anechoic room is a room where you get so much acoustic absorption on the wall that you don't get any reflection. So, and this quartet was surrounded by 6 microphones. And if we think that the sound is going out from a center location, each microphone was covering one of these eight sectors. But when we are in a room, what happened that we have the sound from the stage, and there is a direct sound that is like the sound we hear in the anechoic room, but then we have all the other sound that is kind of bouncing around the wall, and we have the direct sound that is this one, the red one, that arrives at the receiver location as the first one, and then we get all the other sound that are reflected from the room. This is what we call the impulse response, and it's basically the acoustic fingerprint of the room. And each dual connection between a source and a receiver is has a different fingerprint. And this fingerprint, we can see it in 3D. Basically, if we are in stall, the red bit is the direct sound that is really strong. It is the sound coming from the stage. And then in time, we see that we get the blue, light blue, and the yellow reflection that are coming from every direction. So we tried to visualize this, and we basically imported the sound measured as a 3D impulse response in Rhino, and we managed to print the impulse response to show the client. So basically, every bit of the impulse response is covering a different time. So there is direct sound between 0 and 15 milliseconds, and so on. But what's the next step? Let's say that, yeah, we need to put and describe sound and how it behaves in a certain room in a report and in static documents. But at the end of the day, the best way to design with sound is to do it in a room like the Sound Lab, that is this room we have in the London office, as in many other offices. And it's kind of a recording studio, very well sound insulated from the outside, so you don't hear any other thing. There's a lot of acoustic absorption in the room, almost like in an anechoic room, and you are surrounded by 12 speakers, so you get the sound coming from every direction. So if in the real environment you get this 3D sound with the sound coming in every direction, what we do in Sound Lab is recreating the same thing. Basically, with the use of the speakers, we recreate the sound that is coming with a different delay and with a different sound intensity from all the different directions. Then the beauty of it is that we can mix together the sound that is recorded in an anechoic chamber and with the fingerprints of the room. So we can listen to a space before it's been built. So we can have this workshop and session with architects and clients, and the same system can be linked to generative with a computational design software like a Soper, so we can change on the fly the model and listen to it again. And so this is a good feedback for us to understand where to go and discuss it with the clients. Said that, the Sound Lab concept, it's something that can be also brought outside. to recreate 3D sound fields. This is a project we did with a sound artist from New York called Steven Vitiello, and we did the design of, I guess, the biggest 3D sound rig that has ever been produced outdoor, and it was really accurate, and basically it was reproducing some recordings he did in the Amazon forest. Yeah, it was kind of immersing sound, and there was a really good combination between the urban environment, the way people behave in the urban environment, and all of a sudden you find yourself from a kind of an urban jungle that is full of noises that are kind of quite unpleasant, to a real jungle where you can listen to birds and all the other species. So yeah, to wrap it up, I think this is a really important topic for us, and there are a lot of opportunities of including the sound, and not only sound, but all the intangible kind of aspect of design in future architecture design and practice. So thank you very much, and hope you enjoyed it.